So I wanted to welcome you all. My name is Christina Cowden, and I'm an employee and student at MIT. On behalf of the New England section of the American Institute of Aeronautics and Astronautics and MIT AeroAstro, I am pleased to introduce our speaker and his presentation titled Undaunted Exploration, Revealing Our Solar System from Asteroids to Pluto. Dr. Benzel has been an MIT faculty member for nearly 30 years. As a professor of planetary science in the Department of Earth, Atmospheric, and Planetary Sciences, and holds a joint professor appointment in the Department of Aeronautics and Astronautics. He is known as one of the world's leading scientists in the study of Pluto and other areas of planetary science, including asteroids and meteorites. Dr. Benzel completed his master's degree in physics at Macalester College. He went on to receive his PhD at the University of Texas, where his research included the first direct mapping of Pluto's surface. He has received countless awards and honors, including being named an MIT McVicker Faculty Fellow in 1994 in recognition of his dedication to teaching. He even has an asteroid named after him. Professor Benzel is a co-investigator on NASA's New Horizons flyby of Pluto and is principal investigator of the student-built REXUS experiment aboard NASA's OSIRIS-REx asteroid mission that was launched on September 8th. OSIRIS-REx will reach the near-Earth asteroid Bennu in 2018 and return a sample to Earth. The New Horizons mission design was approved by NASA and finally launched in January 2006 on its 9.5-year voyage to Pluto. Professor Benzel serves as a science team co-investigator. His particular interests are centered on understanding the seasonal processes of the shape of Pluto's diverse surface. New Horizons has received many awards, 6 this year, including the AIAA 2016 Space Ops Award. So without further ado, welcome, Professor Benzel.
Thank you, Christine. Thank you all for coming. It's a pleasure to have you here. It's a pleasure to be here. To friends and family and interested people online, welcome to MIT. So I'm going to try to give you a story of exploration, and I'm really aiming this at the students and really try to engage you in this spirit of exploration and give it to you as a little bit of a personal story. But before I say anything else, the most important thing that I'm going to tell you is that this is a team effort. I'm just one member of the team that has accomplished these mission successes, but it takes the entire team. So while you get to see one individual involved, it is this entire team effort, and that's really the most important thing I can tell you. All right, so with that, I want to get to the spirit of what drives us here at MIT, what drives us, I think, in our careers as scientists and engineers, and that's that spirit of exploration. I think it's the thing that binds us, whether we're mathematicians, chemists, management professors, aerospace engineers, or science professors. It's that thrill, that drive to explore that I think is so native as a human being. And that's what I want to try to communicate, and what you can do if you are undaunted in your spirit towards whatever goal you want to achieve. So I'm going to begin with one example of this, which is this instrument that MIT is flying aboard this NASA mission. It's called REXUS. It's this shoebox-shaped instrument. REXUS is a regolith X-ray imaging spectrometer. I'm going to explain what that is. And as Christina said, we launched aboard NASA Atlas V just in September of this year. And the way we accomplished this is we put together and we wove together the best of everything that is MIT. We made the Institute work. And we got 2 departments to work, Earth, Atmospheric, Planetary Science, and AeroAstro to work together in this endeavor. We got our other elements of MIT involved, Lincoln Labs, the Kavli Institute. We brought these together across the School of Science and the School of Engineering. Again, bringing the Institute together, making the Institute work on these kind of endeavors. And then we had to work with outside partners too. NASA management, good luck with that, but it's but in the end it works. The results speak for themselves. And even imagine, one of our partners is Harvard. MIT and Harvard working together. And I have to say that the colleagues at Harvard that I've been working with are spectacular, spectacular people. And in fact, across the project, I've had the privilege of working with spectacular students, spectacular staff. And it really is, at the end of the day, the thing you remember the most and cherish the most is the relationships and the growth and the advancement of the people that you work with. And so that's really the highlight. All right, so REXIS is a part of this mission called OSIRIS-REx. OSIRIS-REx is a sample return mission going to an asteroid named Bennu. It's a near-Earth asteroid, so it's in an orbit that's fairly close to the Earth. Most of the asteroids, of course, are between Mars and Jupiter, but this is one that happens to be orbiting in the vicinity of the Earth. So it's relatively easy to get to. And the reason we're going to this asteroid is based on our own MIT telescopic measurements, we think that this is one of the most carbon-rich asteroids, something that's 4.6 billion years old and contains some of the earliest chemistry of our solar system. The basic elements that not only make up the Earth, but make up life itself. And we get a few samples like this in our meteorite collections. This is a carbonaceous chondrite, and I'm going to pass this around. You can see what we think this primitive material is like. There are meteorite detectors at the door, so you can't go home with it. But we're going to this asteroid, and in the environment of space, we're going to take a pristine sample and put that in a capsule under sealed conditions, bring it into our laboratories, and have a pristine original sample from the very beginning of our solar system, and try to understand what were the basic elements that make up the planets and even us. That's the goal of the OSIRIS-REx mission. So we launched this year. We arrive at the asteroid in 2018, 2 years of operation at the asteroid, and then on the return back to bring back the sample. All right, so the REXIS part of this story is that for the OSIRIS-REx mission held a competition among its member institutions for a student-built instrument to fly aboard the spacecraft. And so this began back in 2010. So this has been a 6-year project. And we began the design project in a class. We did some of the early initial design testing and evaluation in 1683. A class that many people here will recognize. And we're going to start looking at a brand new mission concept in 1683 this spring, myself and Dave Miller. And so stay tuned for the local listings for our offering of 1683 in the spring. But through this long process, what we did was we made with the classes nearly 100 undergraduates, dozens of graduate students, about a dozen master's and PhD theses. We have gone from this early concept into the actual flight hardware. Again, all driven by students and student projects and classes here at MIT. So we've made that transformation from model to flight hardware. And you can see the progression. And very basically, the REXIS instrument comes in 2 parts. The main spectrometer, about the size of a shoebox, contains sort of a pinhole mask at the front. I'll explain something about that in a moment. These are our detectors here that are sensitive to X-ray light. These come from MIT Lincoln Labs. They're CCID 41 detectors. The first time that we've flown one of these detectors on a planetary mission. And then the second little component is called a solar X-ray monitor, or SXM, and I'll explain why we need that little separate component. The reason is that the way REXIS works is that the sun emits X-rays. The sun is always emitting X-ray light. We are shielded by our atmosphere here on Earth and protected. But those X-rays strike the surface of the asteroid. The regolith, or the upper layer of the asteroid, absorbs those X-rays. The individual atomic elements, those individual atoms, atomic shells, absorb the X-rays, the electron levels raise, and when those electrons descend back to their ground state, they re-emit the X-ray, or fluoresce. And what REXIS does is REXIS is measuring the fluoresced X-ray light from the asteroid's surface. Now the catch is that the sun is variable in its X-ray output. So we need this little X-ray monitor to monitor the sun, to see how the sun is changing, so that as we see a different X-ray flux from different parts of the asteroid surface, we know which of those variations are real It's according to the asteroid, and which just happened to be the vagaries of the sun's X-ray performance. So finally, the basic quantum physics here is that the energies of each of those emitted X-rays are revealing to the specific atoms from which did the original absorption. And so we're going to be able to map and measure the abundances of things like oxygen, magnesium, silicon, sulfur, and iron that make up this asteroid surface. And when we do that, we're going to produce 3 data products. The first is to basically map the global properties of the asteroid. You can't read the axes here, but it's an elemental abundance ratio plot. Everyone has one of those at home on their fridge. We'll produce this, which will tell us what kind of meteorite the asteroid is like. Maybe it's like the one we pass around in the room. We don't know. It's one of the fundamental things we don't know. Next is because the asteroid is flying over because the spacecraft is flying over the asteroid's surface, we'll be able to map where we see more abundant X-rays or more abundant fluorescence based on sort of on a hemispheric scale, whether we're on the front side or the back side of the asteroid. And finally, we're going to be able to map the X-ray flux in fine detail using that pinhole mask. It's called a coated aperture mask on the front of the REXIS instrument, because those pinholes cast a shadow onto the detector plane, and we can deconvolve that shadow and the changing shadow across the detector plane to pinpoint where it is that the asteroid is particularly active or particularly abundant in these different elements. And so this is going to be transformative in planetary science. Never before has an instrument of this capability been flown on NASA or any mission. And we're going to change the way that science is done. And it was because of MIT students and the Institute bringing the power of the Institute together in a partnership. And we are going to transform this area of planetary science. And it's all to the credit of the students. Now, it hasn't always been easy. A project like this over 6 years isn't always easy. You have lots of major delivery dates, test dates, review dates where the NASA managers all come in and review your progress. And we could predict the next major snowfall by the dates of our most important meetings and milestones. You need critical parts, so you use reliable shippers. But an SUV runs into a UPS truck, and your parts just happen to be on board. You can't make this up. Not all your testing goes well. We had a vacuum chamber fail, and in the process of the failure in the vacuum chamber, some of our parts were contaminated. Some of our flight-ready parts were contaminated, and because it's a sample return mission and everything has to be pristine, our best parts were no longer usable. We had to find some alternate way of putting the thing together. If you've ever built a flight instrument, you know that you torture your instrument on the ground because it has to survive the vibrations and stress of launch. And so you try to torture it on the ground. And we were successful in finding how our instrument broke. And a consequence of our instrument not surviving the test was losing basically a broken cable in one of our main circuit boards. And not only that, we finally survived all that. We got to the spacecraft assembly site in Denver, Colorado. And we noticed at the last check on the bench, we're literally sitting this far away from the spacecraft, and our instrument produces nothing but noise. And we realized there were some problems in our circuit board design. What a heck of a time to figure out you have a circuit board design problem. That meant we had to take the instrument apart. And to do that, we needed to get into a clean room, we needed expertise and help. We were in the last minute, we got on board, we either fixed it and got on board or we were left behind. MIT Lincoln Labs rolled out the red carpet for us. We were their top priority. We brought the instrument back from Denver. We opened and got it into the clean room, opened it up, did the fix, reassembled it, then we had to go back through all our testing again. Got through our testing, back to Denver, on board the spacecraft. There we are. This was a year ago. This is what we were doing a year ago. All we wanted for Christmas was to get our instrument on the spacecraft. And there it is on December 18th. This is MIT graduate student Mark Chodas and our project manager, Becky Masterson. Fantastic, fantastic people who really made this project work. And there they are mounting the instrument on the board the spacecraft the week before Christmas last year. We're on board the spacecraft goes on board the rocket, and there Rexus goes off on the launch just a few months ago. So we are now flying in space thanks to the amazing cooperation of all these elements here across the Institute of MIT. So this is our first image from space. We have a cover on our instrument. We keep the cover closed till we get to the asteroid. So we're looking at the backside of our cover, so isn't that exciting? But we have an onboard X-ray source, several onboard X-ray sources inside our instrument to calibrate what we see. And so this is just looking at our internal calibration, but this is a real signal from our instrument flying and performing perfectly well in space. So it's really quite spectacular. We're going to be doing ongoing tests for the next 2 years, but in early 2019, we'll be opening up our cover and taking real data. So that's the Rexus story. Maybe I'll take a quick question or two, and then I'm going to get to the main story of Pluto and New Horizons. Any questions on Rexus? So anyway, thank you, Jaime, and the department has been spectacular, and your people have been spectacular in making this work. Yes, Christina. So our instrument, being part of the big spacecraft, sends its data to the main computer of the spacecraft, and then the spacecraft talks to Earth with its regular radio communication. So we get a little storage space on board the spacecraft computer, and every once in a while they let that part of the spacecraft computer talk to Earth and sends it back here to MIT. Yes?
Make an advertisement. We're going to go to Lincoln Lab, and you'll be there, and we're going to review all the work Lincoln Lab did to do that fix and the previous work too. So that's coming up, so read your AIAA.
Well, I'm looking forward to it. Yeah. All right, so let's go on to Pluto. So I'm going to whip you from the inner solar system, drag you all the way out to the outer solar system of Pluto. And a few years ago, you might have known that Pluto got this new kind of label as a dwarf planet, and some people were a little bit upset about that. But as I like to say, dwarves are planets too. That was supposed to be funny. And the key thing that most people don't know if you're not an astrophysicist is that the sun is a dwarf star. The sun is a dwarf star, and we don't love the sun any less. So Pluto is just fine as a dwarf planet. All right, so the Pluto story begins in 1930 with a young astronomer named Clyde Tombaugh. And his job was to be an explorer. He was hired to search the solar system with the idea there might be something out beyond Neptune. And here in February of 1930, images 2 nights apart, he found something moving at a slow rate, indicating it was far from the sun. And that was the discovery of Pluto. Now, in the 1980s, I was a graduate student, and I was perhaps the only graduate student on Earth studying Pluto. And when you have that novelty, you get to meet the discoverer of Pluto. And I'm the guy on the right. Now, we lost Clyde in 1997, but some of his ashes are on board the spacecraft. And so Clyde Tombaugh got to, in a personal way, explore the planet he discovered. We think that's pretty amazing. All right, so the way I got involved in the scientific study of Pluto was that there was a satellite of Pluto discovered in 1978. This is the best we could ever see Pluto before Hubble Space Telescope. And it's just a fuzzy blob, but sometimes that fuzzy blob had a little bump on the side that would change sides over the course of a 6.4-day orbital period. It's the orbital period of the satellite of Pluto called Charon. And Pluto's rotation period is also 6.4 days. And the two bodies are locked in a continuous dance with each other, sort of a face-to-face dance forever. For the Earth-Moon, it's the Moon's face is locked to us, but we are allowed to spin underneath. But in the Pluto-Charon system, it's totally, tidally phase-locked. So what we found, and what was interesting other than that Pluto had a satellite, was that we determined that the orbit plane of the satellite was about to go edge on. Now this is pretty rare because it only happens once every 124 years. That's half of Pluto's 248-year orbital period. And so you're a graduate student in the 1980s, someone has to go spend weeks and weeks and weeks and months at the telescope to try to detect these things. And when you're the graduate student, that's what you get to do. And so I spent hundreds and hundreds of nights at the telescope. And then finally in 1985, we weren't sure about this geometry, but finally in 1985, the first time we detected the satellite going in front of the disk of the planet. And the way we detected that was just seeing a little unusual brightness change in the system. The same thing we do now with exoplanet transits. These were planetary transits, and we were doing them decades before anyone even invented the word exoplanet transit. So this is a standard process now in astronomy. So we saw these transits happening in the Pluto-Charon system, and as the few years went on, the satellite was transiting across different parts of the disk of Pluto. And if we could just simply observe these transits over different parts of the disk of Pluto, even though Pluto is nothing more than a fuzzy blob, we could deconvolve all those different light curves, those brightness variations, into a map of the surface of Pluto. And this is the first map of the surface of Pluto produced before Hubble Space Telescope was even launched. So we were getting an understanding of Pluto even before Hubble. And what we interpret is that we see bright poles on Pluto, this dark equatorial band, but it's not uniform. There's these regions of abrupt contrast. And this says that Pluto must be really interesting, because it's very hard on a planetary surface to get bright, dark contrasts. In fact, it's very hard to see something very bright. That's because space is a dirty place. There's always micrometeorites bombarding. There's galactic cosmic rays, UV photons from the sun, which will turn any kind of bright surface dark in a short period of time. So this suggested that there must maybe be some sort of seasonal processes that are driving the bright regions on Pluto, like Mars has pole-to-pole seasonal variations in its polar caps. But if that's true, then something had to be allowing those seasonal changes to happen. And so the question arose is whether or not Pluto had an atmosphere. And so this question was front and center in the mind of our MIT colleague Jim Elliott, who we lost about 5 years ago. Jim was a pioneer in a technique of something called stellar occultations. And as planets move around the sun, they occasionally pass in front of a distant star. But if you can monitor the starlight as it goes behind the planet, you can see whether or not that planet has an atmosphere. And so this is an event where there was a particularly bright star that Pluto was passing in front of. And what they did was using an airplane, a telescope in an airplane, which could then position itself in just the right place on the Earth's surface to see the event. They noticed that the brightness didn't drop instantly when the star went behind the edge of Pluto, but the starlight dimmed gradually as it went behind Pluto, and then when it came out the other side, it rose gradually. And that's the signal that Pluto has an atmosphere. So the pieces started to come together in terms of understanding all the processes, all the different things that must be going on at Pluto. And the things we think are present there are nitrogen and methane. And if you look at this phase diagram, when was the last time you got to go to a talk and see a phase diagram? This is MIT. All right, so at about 60 Kelvin and a very low pressure, you see that nitrogen is at the transition between solid and gas, and methane is at the transition between solid and gas. Two compounds that like to change places from the solid state to the solid state to the gaseous state. And on Earth, mainly that's water. So on Earth, we have water, and we know what water does on Earth in so many different ways in terms of shaping the Earth's surface. Now we have two compounds at Pluto that have the capability of doing that. And not only that, but Pluto is in this elongated orbit. The Earth-Sun distance is something we call an astronomical unit, or 1 AU is our Earth-Sun distance. Pluto varies in its distance from about 30 AU to about 50 AU. So that's going to give you very different amounts of heating, depending on whether you're close to the sun or far from the sun. And one other thing is that Pluto is tipped sideways in its orbit. And so that means there are times when one of the poles of Pluto has this century-long Arctic summer, while the other pole experiences a century-long Arctic winter. And so we have these very dynamic processes going on Pluto. And we had this all figured out in 1989. So we had, imagine how exciting this was. In a big conference like the American Geophysical Union, we actually got to have a special session on Pluto. And there were 12 papers, 12 talks given in that special session. And we each stood up and gave our paper to the other 11 people in the room. And then we went out to dinner. But each and every one of us was saying, gosh, we've reached the limit of our understanding. And Alan Stern, who became the principal investigator of New Horizons, stood up and said, folks, we need a mission to Pluto. Voyager is just about to get to Neptune. We know how to do this. Why not now, and why not us? And we were barely graduate students or just first-year postdocs. And it was the audacity of youth that started this whole thing. So we began this process, and we built our argument this way, which I now call the pyramid of planetary exploration. But you start with basic surveys that Pluto was found, and we began making physical measurements. And then when you make measurements, you find tantalizing things, and this applies across many, many fields. And as you make these tantalizing measurements and find these amazing questions, you reach a series of questions that have significant consequences if only you could gain their understanding. And with that, you make your argument for a spacecraft mission. So the argument to go to Pluto wasn't that we had never been there before. It was because we had important, amazing scientific questions to ask if we could go there. There are lots of places we have never been before. And so you have to make a better argument than that. And that's what we began doing. So you can read all about this in an earlier this year issue of Physics Today. It is a long, long story. We went to NASA, we got approval, and then we got canceled. We came back, they said, do it a different way. We did it a different way. We got approval, and we got canceled. Approval, canceled, approval, canceled. You kind of get the idea that we were Charlie Brown, and we were just having a hard time kicking the football. But we were undaunted, and we proceeded on. And the next iteration of this was something we called New Horizons. And something amazing happened along the way. We realized that Pluto was a member of the Kuiper Belt. This is a whole new zone of the solar system. It's like another asteroid belt in the solar system that exists out beyond Neptune. Pluto is one of maybe a dozen similar-sized bodies in the Kuiper Belt. So that makes Pluto the most common kind of planet in our entire solar system. And so we weren't just going there to study Pluto, we were going there to understand something very fundamental about our entire solar system. And we got the top ranking priority for a next NASA mission out of the National Academy of Sciences. So with that, we got our mission approval. And the thing that also happened along the way was the improvement in electronics, such that in a spacecraft that would fit right here in the front of the room, the size of a grand piano, we could get imaging capability like this, that in equivalent flyby of the Earth with New Horizons, we would see the campus of MIT. So this is our New Horizons instrument, again, the size of a grand piano. We have our long-range imager, which does those high-resolution images, our radio experiment to get the data back, a spectrometer in the ultraviolet, invisible, and near-infrared called Alice and Ralph, a dust counter. This was actually built by students at the University of Colorado, and two instruments, SWAP and PEPSI, that measure the particle environment, the space environment around Pluto. So here's the first quiz question of the day. What does the New Horizons spacecraft have to have in common with a Motorola flip phone? You remember those? Anyone still have one? Bravo. They're the same technology era. Isn't that amazing? New Horizons is built on the technology of the Motorola flip phone. But you have to remember, the Motorola flip phone and how we got cell phones in our pockets is a story of the miniaturization of electronics. And we came along and we were there beating on the rock over and over again with all our designs as the miniaturization of electronics got better and better and better. And we hit this threshold that coincided with the flip phone and the cell phone right at the time when we had that most important scientific backing for our mission. All right, second trick question. How do you power a mission to Pluto? How do you have electric power on board your spacecraft when you are so far from the sun, solar panels won't work? Radioactive decay. It's even more obvious than that. If you're going to go to Pluto and you need electrical power, you use plutonium. Plutonium has a half-life of about 100 years. And so this is our radioisotope generator. So the plutonium that we load in there generates heat. We convert the heat into electricity. And the encounter, everything we've accomplished with New Horizons at Pluto was done with 200 watts of power. A couple of light bulbs is everything that we accomplished at Pluto. So here's our New Horizons spacecraft on an Atlas V rocket with 5 strap-on boosters, the biggest rocket in the fleet. And it's a really tiny spacecraft on board a really big rocket. So why do we need all that thrust? Well, it's pretty simple, and everyone here probably knows. But you know, the job of the rocket is to give you kinetic energy. That is, take your mass and give it velocity. And so the more velocity you want, the smaller your mass has to be. And we knew from the get-go, from the first time we were designing the New Horizons mission, or our mission to Pluto, that it would have to be a flyby. Because the way it usually works is the first time you go anywhere, it's a flyby mission. The first missions to Mars, the Mariner spacecraft, were flyby missions. And so the reason why this was a flyby mission is that it's very far to Pluto, as I'm going to give you an MIT illustration here in a moment. It's very far to Pluto, and you want your instruments to still work when you get there. And being selfish scientists and engineers, we want to still work when we get there. And so we wanted to have a spacecraft that went at the highest possible velocity, so everything was still around and working when we got there. And so that just means you have to keep your mass really low so your velocity is very high. And it turns out, so it has to be a flyby, and it turns out if we wanted to load enough fuel and add enough mass so that we could stop and go into orbit at Pluto, the amount of mass we'd have to carry in terms of propellant then exceeds the launch capacity of any rocket. And so there was just simply, the equations just don't close. And so it had to be a flyby mission. So after all that, we finally got off the launch pad in 2006. We had our flyby of Jupiter, which we used for a gravity assist that enabled us to get to Pluto 2 or 3 years faster than if we were going there directly. And of course, being scientists, we turned on all our instruments just to make sure they worked. But we got a fantastic set of scientific results out of our Jupiter flyby. And then we continued on our total journey of 3,463 days. And the reason I know it's 3,463 days is I counted each and every one. And we had to go a distance of 10 to the 9 kilometers. There are a lot of engineers here, that's 10 to the 18 microns. It's a long distance to Pluto. And just to give you an illustration, this is the MIT illustration of how far it is to Pluto. Imagine in the infinite corridor that when you come out of Lobby 7 and head towards Building 8, you put the sun here and Pluto there. Where do you put the Earth? Where do you put the Earth? Well, it turns out the Earth is about 10 steps away. There you go. Sun to Earth. And you know what? On that scale, the sun is just a little bit bigger than a baseball, and the Earth is just a tiny BB. Think about that. The next time you walk down the infinite corridor, the sun is this size, the Earth is even smaller than this. And I've made multiple proposals across the Institute that we ought to put a little model like this in the infinite corridor, and I've been turned down every time. And I am undaunted that we're going to make this work. So most recently it was Chancellor Grimson who turned me down. And if anyone knows Grimson, go talk to this guy and say, we need to put this here. So remember that. Next time you're in the infinite corridor, you take your first few steps down the corridor, you're at the Earth, and you've got to go all the way down to get to Pluto. And that's how far we traveled. So we finally got close enough to resolve the system with our long-range camera. And what's interesting is Charon is about half the size of Pluto. And if they're equal density, now we know they're relative densities and things like that. But it turns out the center of mass of the system is in the space in between the two bodies. So it's almost like a double planet system. This is the sort of orbital motion we see in double star systems. So this is a great 801 physics problem to calculate the barycentric motion of the Pluto-Charon system. Anyway, there it is. It's just a great, great little physics movie. All right, so finally we're getting closer and closer to Pluto. Pluto rotates very slowly, 6.4 days. We can only go by one side because it's a flyby. And so we chose the side that we knew had the greatest contrast, which ends up being the side that we found is heart-shaped. But meanwhile, the side that we had mapped back in the 1980s was the exact opposite side, just as it turns out. But as we got close, we can ask the question, how did we do back in the 1980s? And here's what Pluto looked like from New Horizons in 3.2 days before we arrived. And we would have to account for the fact that the sun geometry has changed between 1988 and 2015. And you know, we kind of get a B+ or maybe even an A- on our initial mapping of Pluto. So we're pretty happy about that. All right, so I told you Pluto is tipped over on its side as it orbits around the sun. And so that means because the Earth is, of course, close to the sun, we're coming at the Pluto system almost like a bullseye pattern. And so we have to optimize how we're looking at Pluto, how we're looking at Charon, and we now know of 5 satellites in the system. So we're trying to look at all the satellites. And so we have to make this orchestrate exactly how the spacecraft is going to do all its pointing. So I'm going to show you a little visualization here. This is like the viewfinder of the camera up here in the corner. And either the video is going to work or it's not. And since it doesn't, I have to do a little switcheroo here. No surprise. And so just watch the spacecraft. Everything with the spacecraft is done with thrusters. We have little thrusters running on hydrazine. So we have to fire a little thruster to move the spacecraft and then the opposite thruster to stop it. And so all of these are calculated thruster firings. And you're going to look at what you're going to see is like a ballet. And you wonder what we did for 9.5 years on the flight out to Pluto is we perfected this ballet. And I'll come to that again in a second. So here we see we're coming into the system. You can see it looks like this bullseye. I don't know if we can kill the lights. Probably not so much. We're coming into the Pluto system. Here's the viewfinder with different instruments making their measurements. And each one of these maneuvers, again, is a finely tuned ballet of making these measurements. So we've just gone by Pluto. We're sampling the space environment. We're now watching Pluto occult the sun, that same kind of experiment that Jim Elliott pioneered, we had New Horizons do at Pluto. And we're going to do the same thing with Charon. And we'll look at the satellites on our way past. So this is about the last day. This is about one full day. We were actually taking data on Pluto for about 6 months in and for several months after. But that one key last final day, of course, was the main event. All right, so imagine the decades of effort to get a mission to Pluto. Finally getting to the launch pad. Flying for 9.5 years, practicing everything we could, trying to make it perfect, but realizing human beings are human beings. So we had 9.5 years of flight. The spacecraft is now 4.5 hours away from the Earth in terms of the radio communication delay. 4.5 hours out, 4.5 hours back. There's no time. If something goes wrong, there's no time to get the information back, diagnose it, get a fix uploaded. Everything has to work. It's a flyby. And we get one shot and one shot only at this. And so in those last hours, the only thing we could do is simply buckle up and wait. And we were waiting for that signal, and we did it. I still find it hard to believe. As far as we can tell, even more than a year out, everything worked perfectly. As far as we can tell, everything worked perfectly. And we did it. We found Pluto to be absolutely spectacular, as you've seen. Absolutely spectacular, as you've seen. And not only did Pluto deliver, the science team delivered. Most missions within 90 days submit their results for publications. We published our results in 90 days. So I'm going to give you a tour of the results. And we're going to start with this famous heart-shaped region on Pluto that we call Tombaugh Regio, named after Clyde Tombaugh, the discoverer of Pluto. We're still in discussions with the IAU to get all these names fixed. It's just a long process. And the left lobe of Tombaugh Regio, this region called Sputnik Planitia, or plain, and we named it after explorers. A lot of the places we named on Pluto are after famous explorers. Again, this theme of exploration. And Sputnik Planitia is very interesting because it's young and crater-free. Normally, planetary surfaces, if they sit there very long, will just collect craters over time. But even today, we have yet to find a single crater on this ice sheet. And that tells us that something must be going on to make it fresh and smooth and erase craters. And I'm going to try to give you a story for what we think is happening there. So we're going to look at various regions here on the ice sheet of Pluto, beginning at the top part of the ice sheet. And what we see are flow patterns. We think this ice is nitrogen ice, and we see flow patterns in the ice. There are active flowing glaciers of nitrogen on Pluto. Active glaciers on Pluto, made out of nitrogen ice. In this room, at roughly 300 Kelvin, nitrogen is a gas, but at 50, 60 Kelvin, nitrogen is a solid. Now we see the frozen nitrogen ice glaciers on Pluto. And something that's very interesting, that if you have a layer of nitrogen ice that is tens of meters thick, you start looking at the pressure under the base of that nitrogen ice layer, and you start nicking this liquid nitrogen part of the phase diagram. And we think under the pressure of the nitrogen ice, liquid nitrogen exists, and that glacier is actually floating on this layer of liquid nitrogen. Physics and nature and phase diagrams are absolutely amazing. They can do amazing things. And nature, it just keeps proving that nature is so much more creative than we can possibly imagine. The ice sheet looks like convection cells. You make oatmeal in your microwave, and you look at it, take it out of the microwave, and it looks like it has these little cells in it. It looks like your oatmeal. And we said, oh my gosh, could that be convection? Those are convection cells in your oatmeal. Could that be convection? And the answer is yes, we think it is convection. Because we stop and say, okay, the Earth has heat coming out of the interior. The Earth is very large, a very good insulator, so the heat doesn't get out very well. Pluto is much smaller, it cools off much faster, but it still has about 2% of the heat flux from its interior that the Earth does. And so we said, okay, could that be enough from underneath to warm the bottom? So you do a calculation, something called the Rayleigh number, which is just basically tells you, do you have the conditions that are right for convective flow? And it depends on the temperature gradient and the depth of your layer and all the thermal properties of what's going on in that layer. And when we do the calculations of putting in all these reasonable parameters, we find that the base, if the ice sheet is now just a few hundred meters thick, at the base of the ice sheet, where the temperature is only 40 or 50 Kelvin, that's enough heat to drive convection. Again, this is nitrogen. It doesn't take a lot of energy to make nitrogen go to the liquid phase or convect. So it's a different physical regime than we're used to. And so we've basically calculated and determined that, yes, this can be convection. And if you don't believe the math, all you got to do is put a little canola oil in a pan on the stove and watch. And you can see these kind of convection cells that are amazingly like what we see on Pluto, just in something as simple as oil on a pan on the stove. All right, so again, nature is more creative than we can possibly imagine. One other thing, I don't think it's going to show up in this projection, but at the center of Sputnik Planitia is a region that has this sort of circular outline. And we've been scratching our heads since day one, literally, as to wondering whether there was an underlying crater there. And when you have a really big crater on a planetary surface, you call it a basin. And it's about the same scale as large basins on the Moon and on Mercury. This is Caloris Basin on Mercury. And so we've been scratching our heads, wondering whether that could be an impact crater that simply has been later filled in by the nitrogen. It's a great place for the nitrogen ice to fill in. And then we noticed something about it that said, wow, we think that this region of Pluto has something we call a positive gravity anomaly. All right? In other words, a gravitational bulge. And when we calculate what could be giving that anomaly or giving that gravitational bulge, we actually think that there has to be something, some dense layer underneath the surface of Pluto that's pushing up, and that's that density from below that's giving this gravitational mass anomaly or this gravitational bulge. And when we do all the calculations, the pressure and temperature and what's available, the most likely thing is water, H2O, in liquid form, maybe slushy form. But just within the last couple weeks, we published this result in Nature, basically the discovery of evidence, not the discovery of an ocean, but the evidence that there is a liquid ocean underneath the ice surface of Pluto. Absolutely amazing. So why is it we think there's this gravity anomaly and leads to this ocean hypothesis? Well, it turns out that Sputnik Planitia is lined up exactly on the tidal axis between Pluto and Charon. And that could be random. In fact, you kind of do the area calculation. There's a 5% chance that's random. That could happen. But if you just simply have a positive gravity anomaly, the most likely outcome of that anomaly is to rotate yourself either pointing toward Charon or away from Charon. And so the fact that this special feature on Pluto is so precisely aligned with the tidal axis tells us, it speaks to us and says, gravity anomaly, gravity anomaly, gravity anomaly. And that's the basis for the news about the idea of an ocean underneath the surface of Pluto. All right, so Pluto not only has ice sheets, it has mountains. We're going to zoom in on the mountains. These are a set of mountains named after Norgay, one of the co-climbers or the first to the summit Everest. It's the first Nepalese person ever commemorated on a planetary surface. So these Norgay mountains are about 4,000 to 5,000 meters high. They're as high as the Rockies, as high as the Alps. And we think they're made of water ice. So again, we see water ice everywhere on Pluto as well. We think they're made of water ice because if it was nitrogen or methane, they wouldn't have enough strength to hold themselves up. So that's why we think these are water ice mountains. And one of these, named after the Wright brothers, is circular, and it looks like it's built up layer by layer by layer, like a shield volcano. And we think maybe this is successive flows of water from underneath building up this large volcanic, what we think is a volcanic feature on Pluto. A volcano, ice volcano on Pluto. And we know it can't be very old because there's only one crater on the side. Absolutely amazing. So something I'm doing with a graduate student in EAPS named Alyssa Earle is we're looking at the long-term cycles on Pluto, long-term climate change on Pluto. And very briefly, right now when Pluto reaches its closest point to the sun is over the equator, and Pluto's tipped over by about 120 degrees. So the Earth undergoes obliquity oscillations called Milankovitch cycles. Pluto does the same over about 3 million years. And it turns out about 1 million years ago, Pluto was at its minimum in its obliquity cycle, and the poles were pointing right at the sun when it was closest. And basically, we're getting times when there are super seasons on Pluto, when the Arctic summers align with the closest point to the sun, and the pole aligns most directly at the sun. And if we look at the atmospheric pressure at these different epochs on Pluto, we see that about 1 million years ago, we can calculate that the pressure, atmospheric pressure on Pluto, maybe got to be as much as what we see on Mars. And the thing that spurs our thinking is that we see evidence where there was once liquid flowing on the surface of Pluto, probably liquid nitrogen. That Pluto got warm enough pressure that nitrogen can flow as a liquid, a little stream channel here. These things look like kind of like the ice outside in about April, and even what looks like a flat frozen pond of liquid nitrogen. And so we think there are these long-term climate cycles on Pluto, not just the orbital seasons, but long-term seasons on Pluto. All right, so Pluto's gotten all the attention. What about Charon? It's half the size of Pluto. It would like some attention too. And we had a fundamental guess as to whether we would see Charon as an old, heavily cratered surface, like Rhea, satellite of Saturn, or some younger surface like Ariel, satellite of Uranus. I was guessing this, but I was wrong. It turns out that Charon looks relatively crater-free, and what we think happened is that Charon formed in a giant impact into Pluto, just like the Earth-Moon system. Initially, when Charon formed, it was slushy, but as it cooled, just as ice, when water ice freezes, it expands. And in that expansion, sort of a big expansion crack here, in that expansion, most of the surface got smoothed over, and as it froze out. We now think Charon is completely frozen out. We also were surprised to see this red polar cap on Charon. And what we think that is that some of the methane in the atmosphere of Pluto escapes. In the process of escaping, those methane molecules go to the coldest place on Charon, which happens to be the poles. When we look at these long-term climate cycles, there's a zone at the poles of Pluto that happens to be the coldest. When the methane ice gets trapped there, the ultraviolet radiation from the sun, the galactic cosmic rays turn it red. And so we think that this is sort of an exchange process between Pluto and Charon, giving the red polar caps of Charon. So as I said, there's a full satellite system of Pluto, 5 satellites, and this is a near-infrared spectrum that's coming up here, near-infrared spectrum that tries to decode the compositions. All of the satellites appear to be made of similar material, water ice. And we think that's consistent with an impact, sort of another Kuiper Belt object, hitting Pluto early in its formation, splashing off this material, and giving sort of a uniform composition to the whole satellite system. All right, so this is our farewell image to Pluto, but I want you to stop and think about what this image represents. This is a total eclipse of the sun behind Pluto. And all those other images, in principle, if we had a super-duper telescope, space telescope from Earth, we could be seeing Pluto in fine detail. But not this. You have to be on the dark side of Pluto, the backside of Pluto, in order to see an image like this. And what's amazing about the atmosphere of Pluto is it's blue. It has nitrogen. The atmosphere outside, if it's ever sunny, is blue because of nitrogen. And so who knew that Pluto and the Earth share this same affinity for blue skies? Pluto is absolutely amazing. So we are a flyby. We're going to keep on going. We will leave the solar system. In about 20 years from now, the energy of our plutonium will run out. We won't have enough energy enough to power our heaters. The spacecraft will freeze to death. It will happen. But on the way out, we're passing through the Kuiper Belt. And we've identified, thank you to Hubble Space Telescope, we were looking with the MIT Magellan telescopes. Ultimately, we found a target with the Hubble Space Telescope. The target we found has the household name of 2014 MU69. MU69 is about a 50-kilometer Kuiper Belt object, kind of regular, ordinary, run-of-the-mill, typical Kuiper Belt object. We couldn't be happier because we're going to see what one of these native objects looks like. In comparison, this is the comet named CG that Rosetta was studying. So amazing object, and we think that the Rosetta comet probably is a sample from that part of the solar system as well. So we're going to kind of do this comparative planetology between comets and Kuiper Belt objects. So we're very excited scientifically about that. This is the kind of results we expect for our imaging system at MU69, our target. And this is the kind of mission profile we're now in the process of designing for when we get there in January of 2019. So you may have noticed something in the news when Pluto and New Horizons got to Pluto. NASA was pretty unhappy back in about 2012 when they landed on Mars and they got all these web hits that it knocked their website offline. Oh, we even got the Google Doodle and stuff like that. Really great stuff, right? This is what happened when we knocked the NASA website offline again. We were really happy. NASA was not, but we were. Pluto's gotten a lot of attention, as you've seen in a lot of different ways, a lot of different awards, as Christina mentioned. The Goddard Trophy, Schweigert Exploration Award, Museum, Air and Space Museum, Aviation Week Laureate Award. Thank you to AIAA, Space Pioneer Award, et cetera, et cetera. A lot of great hardware. But again, these are team awards. These are team awards. So you might remember or might know the story of in 1991, there was a stamp that was issued. There are stamps for the entire solar system that were issued. And this was the best they could come up with for Pluto. Well, thanks to New Horizons, we have real stamps. So you can get these at your post office. And anyway, that's for you. If you sit in the front row, you get the stamp. Anyway, so you can have these. So these will be on my Christmas cards. Trust me. All right. So here's something that happened that caught us by surprise, and we're very proud of it. As we were in the midst of all this media attention, the reporters noticed, they said, I just talked to one of the chief scientists of the mission. It was a woman. I just talked to the chief operations manager. It was a woman. And we're like, yeah. It turns out 30% of the New Horizons team are women. It's the highest percentage of any NASA mission yet in history. Now, we're not quite there yet, but we are very proud of where we got. And we got there not because we were necessarily going out trying to bring in women into the project. We were just hiring the best people. So I think that says a lot for our programs at many universities that we are training that next generation. But MIT has its role as well. These are students of Professor Elliott, and they include the two deputy project scientists, Leslie Young, whose dad is Larry Young. Is Larry here? So our Aeroastron's own Leslie Young, and Kathy Oken, also a graduate of this department of Aeroastro, and Eeps, who's a graduate across both departments, are deputy project scientists on the New Horizons mission. So MIT has had an incredibly important role here, and even really specifically a credit to Professor Jim Elliott. And over in Eeps, we have a scholarship fund, a fellowship fund for graduate students named in Jim Elliott's honor as a Pluto scientist and a mentor. And if this is of interest to anyone, the flyers and the brochures are at the doors. But I'm happy to talk to you about that. So thank you for thinking about that and remembering one of our own pioneers here. Okay, so to end, I said this is all about the spirit of exploration. And I'm really enamored with this nickel. This is the back of a Jefferson nickel that came out a few years ago. And what I want you to remember is that just, in the grand scheme of things, not very long ago, just 200 years ago, the frontier of exploration was going across the continent of North America, Lewis and Clark. And in just 2 centuries, we have pushed the frontier of exploration not to be just across a continent. We have pushed the frontier of exploration to be across the solar system. Only one generation gets to do that. And we are that generation. It's just amazing. It's just amazing to be in that generation. And it's an absolute privilege to have been a scientist and an engineer at the right place and the right time in history to make this first voyage across our solar system. So we're really proud of all that, but I think what we're most proud of is the attention that New Horizons got, and particularly the attention we got from our younger people. And we hope that New Horizons has delivered the Apollo moment for an entirely new generation. And we'll kind of know that when you guys arrive at MIT. So with that, as I said at the very beginning, this is a team effort, and on behalf of the team, thank you very much for coming. So I'm happy to take questions, and I can stay as long as you like. And so if you have a question, I'll repeat it so that everyone can hear, and then we'll go from there. Yes, sir.
Personal stance on Pluto becoming a dwarf planet.
I am perfectly fine with Pluto being a dwarf planet because dwarves are planets too. The dwarf planets outnumber the planets. So we're going to win. We're going to win. Yes, sir.
So if its primary mission finished, what do you see as the next major exploratory space mission?
Okay, so the first question about Pluto being a planet. This is, what's the next major exploratory mission to Pluto or something else?
To anything.
Anything.
Yeah.
So I think the thing that has the most traction right now is a mission to Europa. It's an icy satellite of Jupiter. And there's evidence at Europa that there's a liquid ocean underneath the surface of Europa. Also, we see geysers of water ice shooting out of the crust of a Saturn satellite named Enceladus. And so that's another very exciting destination. We have a moon of Saturn named Titan that has a thick nitrogen atmosphere that may have carbon compounds or nitrogen compounds and even carbon compounds in it. That might be a place for life. At Mars, we know that water has existed or does exist at Mars. And the question is did life ever arise on Mars? So I think those are some of the key exploration questions. I would like to go back to Pluto with an orbiter, but I think it's going to be these guys that are leading the mission because I think it's a few decades away again before we're going to get back to Pluto. Yes, question?
I was reading about a new movement for satellite swarms, sending hundreds or thousands of small satellites to a planet, for example. What could we use something like that for?
Okay. So the question is about basically CubeSat swarms.
Or even, yeah.
All right, well, you need to take 1683 in the spring if you're an MIT student. We're going to look at that. So CubeSats, for people who might not be familiar, are basically very small, inexpensive individual satellites. And so imagine sending up into space 1,000 iPhones or something, the capability of an iPhone. What could it do? I think there's a whole suite of possibilities. I'm interested in asteroids that come near the Earth, and you could set up, I call it a paparazzi approach. That an asteroid's coming by the Earth, you send up this paparazzi swarm of iPhones, basically, as CubeSats, let it fly through the swarm, and you take all sorts of data from it. So anyway, I think there's a huge number of opportunities. Jaime?
How did the Hubble telescope inform the Pluto mission?
How did the Hubble, yes. Yes.
Follow up on that, now we're looking at the James Webb telescope being launched.
So how did the Hubble telescope inform the Pluto mission? Remember, when we were doing those maps with the transits of the satellite, because they're locked together, we could only map one side. So Hubble allowed us to do the full rotational mapping. And in fact, it was Hubble that saw this bright, dark contrast that proved to be the heart of Pluto. So it was Hubble that actually, the results from Hubble, that actually guided us and said, this would be a very interesting place to have our closest flyby. So it was really the initial reconnaissance of how to send our spacecraft that came from the Hubble data. With James Webb, the interesting thing is now we know Pluto is very complicated and is likely changing. And with the resolution we're going to get with James Webb, we can look at Pluto. We don't have to wait for every flyby. Every time we can get a turn with James Webb and look at Pluto, we're going to be seeing its seasonal changes. So in meteorology and atmospheric science, we call it synoptic measurements. We'll be able to do synoptic measurements of the long-term climate seasonal changes on Pluto. So I think James Webb is going to be very exciting in that way. So yeah, question in the back. Yes, sir.
What's your take on these companies that are trying to mine asteroids?
Okay, mining asteroids. I think it's visionary, with caution. I think that someday that can and will happen. I think it's 50 years to a century away. I don't see it, perhaps in anyone's lifetime in this room, as being a commercial success. I would love to be wrong. The major hurdles, what are the major hurdles to it? I think it's just operating in space. The fine detail that you need, in order to scoop up material, process material. The technical details of actually accomplishing that, let alone the economics of bringing something back that actually is worth the investment of the cost up front. I just don't think the system closes. I don't think the equations close. And I think people who think they will are just overly optimistic. They're visionary, and I admire them, but I think there's a dose of reality that they're missing in these kind of events. So more power to them if they want to invest their money in this, because that will ultimately make it happen. But I still think it's a very long time away. Question in the back. Yes, sir. Yes.
Congratulations for this great achievement.
Thank you.
It's fantastic and really great. I have a question since you are such an expert. Do you have any information about science fiction predict the exploration to Pluto?
Oh, science fiction predicting the exploration of Pluto. There are some books, there's science fiction books about Pluto. I think there's one I have in my lab. It's on my shelf because it's so fun. I think it's called The Ninth Planet. I don't remember who the author is. But yeah, there's fun things. But I don't know, maybe it was bad guys hiding out on Pluto or something like that. Anyway, I didn't bother to read. The cover was really cool. But so yeah, the extent that Pluto shows up in science fiction, I don't know. Thank you. Let's see. I'll go here and then I'll come over to you. Yes, sir.
How do you prevent the New Horizons spacecraft from colliding into asteroids?
Oh,
Because it passes through
so the question is, how do we prevent a collision? At 30 kilometers per second, which is our velocity, a grain of sand will destroy the spacecraft if it hits in the wrong place. So that was our biggest worry. We were flying through the Pluto system, and it has all these satellites. All it takes is some impact to make a crater on one of those satellites. Lots of debris out in the system that we don't know, we can't see. And we hit it. So we were doing exhaustive searches on our way in to make sure that Pluto didn't have rings, and we didn't run into the rings. So largely, thankfully space is big and space is empty. And everything we calculated said our chances were really small, that we won't run into something, but they weren't zero. And I think that was the biggest worry we had. There would be something unforeseen in the Pluto system. The spacecraft would run into it, and that would be it. We wouldn't hear from it again. So we had downloaded, before the encounter, we downloaded everything we could. And we got the highest priority, after the encounter, we got the highest priority data off the spacecraft right away. And we're still flying, everything's flying great. But yeah, no, it's nothing we can do. In essence, nothing we can do. Just do the calculations, see if it works well, and go from there. Yes, sir.
So with virtual reality becoming a popular thing, would you send a 360 camera into space so you can see
Wow.
directional?
Question, would we send a 360 camera into space? They've flown IMAX systems on the shuttle and space station, I believe. So I think you could see that in IMAX. But yeah, let's go. We could be the producer of the first IMAX film at Pluto.
Yeah, you could use like a Google Cardboard.
Why not? Use a Google camera. Why not? I love that idea. I love that idea. Okay, a couple more questions. Yes, sir.
So you said the proposal to visit Pluto was shot down 6 times, but the 7th time it got
It's
the highest marks from
Yes.
the what was the
National Academy of Sciences.
There you go. So what was the change of heart? Was there friction because of the lack of sort of doubt of scientific worthiness? Or
I think the limitations were making the scientific case, because lots of priorities, lots of things we want to do. So it's really, does it have priority over all the other things we want to do? I think that was one. Secondly was, could we technically pull it off? And I think those were really it. And it was really a technical challenge and a scientific priority challenge to get the mission to Pluto. Anyway, and there were other factors involved of whose congressional district will get the funding and things. Imagine that, right? Anyway, but look at the Physics Today, April issue of Physics Today has the story in there, and it doesn't hold back any of the details, and they're kind of tough. I read it, and I had a real hard time reliving a lot of that, and but it's all very well documented. All right, who wants the last word? Okay, last question. Yes, sir.
The Kuiper Belt?
Yes, Kuiper Belt.
How does the density, it looks like there's a lot of stuff in
Yeah.
there. I know it's a very
Right.
large volume of space, right? How does the density of objects there compare with like the belt?
The asteroid belt.
Between Mars and Jupiter?
So the question is about the density, population density of the Kuiper Belt versus, I think they're relatively comparable, the torus of the Kuiper Belt. I've never done the calculations. I'm going to assign that as a homework problem. The volume of the torus that is the Kuiper Belt is much more, because of the greater radius, of course. But the density, the abundance, the population is much greater than the asteroid belt. In the asteroid belt, remember, everyone knows the Star Wars scene, flying through the asteroids, and the best line in the movie is, "Asteroids do not concern me, Admiral." The best line in the movie. Anyway, the real asteroid belt is, there are 1 million asteroids 1 kilometer and larger, and their average spacing is 1 million kilometers. So it's actually not hard to fly through the asteroid belt. But we did do the calculation to make sure it would be very embarrassing to run into something that we did know, to get back to your question. So I think they're comparable, but actually I haven't done the math, and I'm going to assign that as either as a take-home in-class quiz or problem set. That's a really good idea.
Well, thank you.
Thank you. Oh, all right, thank you.